Warning: ethanol, ethyl acetate, and acetic acid are highly flammable. Sulfuric acid is highly corrosive. Lab coat, goggles, and gloves are mandatory. Today we will be making some ethyl acetate, starting from acetic acid and ethanol, by means of a classic Fischer esterification reaction. For this experiment, we will be using 60 grams of glacial acetic acid, 100 ml of 95% ethanol, and 2 ml of concentrated sulfuric acid. First, the ethanol is placed in a clean and dry Erlenmeyer flask. Since water is produced as a byproduct in this reaction, the use of dry ethanol would be highly convenient. However, regular ethanol will also work. Then, the glacial acetic acid can be slowly added to the reaction mixture under constant stirring. And finally, the sulfuric acid is added dropwise to the reaction mixture. The solution can be then homogenized for a while. In the meantime, a male to female adapter is attached to the reaction flask. A small reflux condenser is then attached to the system. And finally, a nice and steady flow of water can be established through the condenser. The reaction mixture is then heated up to reflux. In the meantime, let's describe the reaction mechanism. As we have said so far, the reaction taking place can be described by means of a Fischer esterification reaction. First, the electrophile, in this case acetic acid, is involved in an acid-base reaction with sulfuric acid, leading to the formation of a highly electrophilic carbon atom. Then, ethanol, which is working as a nucleophile in this reaction, attacks the electrophilic carbon atom, leading to the formation of an intermediate complex bearing 3 hydroxy groups. This is then followed by means of a general proton transfer reaction and an acid-base reaction involving the hydrogen sulfate anion, leading to the regeneration of the catalyst, sulfuric acid, the formation of our product, ethyl acetate, and the release of a water molecule. In this case, it's interesting to notice that all reaction steps involve equilibrium, which actually means that the reaction won't reach completion unless we remove one of the products, either ethyl acetate or water. This is indeed the reason why we almost always use a large excess of one of the reagents. Usually the alcohol, which is usually cheaper and easier to remove, to further enhance the formation of the final product. Obviously, another way to solve this issue would be to remove one of the products, and usually the strategy involves getting rid of the water through different techniques, such as the use of a Dinner Stark apparatus. Anyway, let's go back to the experiment. After heating for a while, the system started to reflux. The solution should be then allowed to reflux for a total time of 1 hour. After this time, the reaction should have reached equilibrium, and it can be cooled down to room temperature. At this point, we should have a mixture of ethyl acetate, water, and reacted ethanol and sulfuric acid. Now we will isolate our product by means of simple distillation. A distillation head or T-head is then attached to the system. And finally, a simple condenser is attached to it. After a while, the vapors will reach the T-head and the condenser, and the first drops of distillate will start to be collected. The distillation should be continued until about 20 ml of solution are left in the flask. At this point, the distillate should contain ethyl acetate, ethanol, water, and traces of acid. Now we will further purify our product by means of liquid-liquid extraction. The distillate is placed in a clean and dry separatory funnel. It's then washed twice with a sodium carbonate saturated solution. This step should get rid of any traces of acid left within our product. The aqueous phase can be then discarded. The resultant organic phase is then washed with a saturated brine solution. This step should allow us to get rid of any remaining salts and polar species, such as ethanol, from the organic mixture. Once again, the aqueous phase can be then discarded. The resultant organic phase is then collected in a clean and dry beaker equipped with a magnetic stream bar. As you can see, we are left with a kind of cloudy solution, which indicates that it contains large amounts of water. To solve this issue, we will add anhydrous magnesium sulfate, which should remove the majority of the water present within our final product. Indeed, as we can see, after adding large amount of magnesium sulfate, the solution clears up, which means that most of the water has been successfully removed from the solution. The resultant suspension is then filtered and the solution is collected in a clean and dry round bottom flask. Alright, so at this point I have obtained a total mass of 97 grams of ethyl acetate, which is way above the expected yield. This indicates me that actually the ethyl acetate is far away from being pure, and it's likely to contain large amounts of ethanol as contaminant. Indeed, I've decided to take several Raman Spectra to see what was going on. Alright, so in this case we are looking at the Raman spectrum of ethyl acetate just before distillation. In this case, we can clearly see some Raman signals corresponding to ethyl acetate, the 380, 634, 849, and 1000 and something. So we can clearly conclude that we have actually made some ethyl acetate. However, as expected, we also see some characteristic Raman peaks, in particular the 880 and the 1460 signals, which corresponds to ethanol. Actually, this indicates the presence of unreacted ethanol. Alright, so now let's compare the previous Raman spectrum with the Raman spectrum of the ethyl acetate solution just after distillation, which is shown in red in this picture. As we can see, there is a significant decrease on the Raman peaks or Raman signals corresponding to the ethanol, as we have said so far, and obviously a relative increase of the Raman signals corresponding to ethyl acetate, which means that after distillation we have enhanced the amount of ethyl acetate with respect to the amount of ethanol that was originally present in the solution. Alright, so finally let's compare those spectra with the Raman spectrum of the ethyl acetate solution obtained right after the liquid-liquid extraction. As we can see, there is a slight decrease on the intensity of the Raman peaks associated with ethanol, but this decrease is not as significant as the previous one obtained with distillation. And therefore, we could conclude that actually the most successful technique to get rid of the majority of the ethanol is actually distillation. Alright, so now we know that we have ethyl acetate in addition to traces of ethanol. In a future video I will try to further purify the ethyl acetate obtained by means of fractional distillation.
Thanks for watching.